Hello everyone, thank you for joining us today. Today my colleague Mahmood and I are presenting the third part of this permanent magnet motor design webinar series, which will focus on the topic of generating sinusoidal back EMF. We will also focus on simulations carried out by one of the products developed by EMWorks during this webinar. Firstly, let me introduce us. My name is Cal and I'm working as an account manager for EMWorks. I primarily handle commercial sales and marketing activities for our company. My colleague Mahmood is our in-house motor design expert. He is working as a senior product manager and leading the team for the development of our motor visit software. Feel free to write down our details to email us afterwards for any inquiries. You can also connect with us over LinkedIn. Moving on to the agenda of today's presentation, we will be discussing briefly about various products offered by EMWorks before moving on to the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks and how can you request for a trial license. EMWorks offer 4 products with various add-ons covering frequency range from DC to light. Our first product is called EMS, which is used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, actuators, circuit breakers, transformers, and electrical machines. Our second product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is called EMWorks 2D, which offer 2D static analysis and covers simulation of planar and axis-symmetric geometries. Our latest addition is Motor Visit software, which is template-based motor design software. It offers analytical and finite element analysis of BLDC motors. We also offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, my colleague Mahmood will use EMWorks 2D product to showcase you few simulations. Before moving on to the technical part, I would like to inform about our licensing structure. EMWorks offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the programs, our licensing structure is usually annual based. The topic for today's presentation is generating sinusoidal back EMF. This is the third part of the motor design webinar series. Please check out our EMWorks webinar page to see the previous 2 parts of this series. Before moving on to the technical part of today's webinar, I would like to highlight few points. Kindly mute your microphones to avoid any background noise. You can use the GoToMeeting chat window to type in your questions, and we will answer them at the end of this presentation. A webinar recording will be sent to all the registrants in few days. Now I would like to request my colleague Mahmood to take over and present the next part of this presentation. Thank you.
Thank you, Cal. Hello, everybody. Let me just share my screen. Okay. Cal, please, could you please confirm that you are seeing the screen?
Yes, we can see, Mahmood. Thank you.
Okay. Hello, everybody, and thank you for joining us today in this webinar. As my colleague mentioned, this is the series of webinar regarding the permanent magnet motor design, and today we are gonna discuss about how we can generate a sinusoidal back EMF in permanent magnet motors. So I'm gonna start presentation right now, but if you have any questions, please feel free to write down on the chat box, and we will answer it at the end of the presentation. We talked about permanent magnetic motor importance before. So the agenda after this talk is going to be like, we are going to start with introduction about the PM motor. Then we are going to discuss some small part of the operation and principle of operation. Then we will model and simulate the motor with our software, and we will discuss the result at the end. At the end, after conclusion, we will answer the questions that you may ask you may want to ask during the presentation. Okay, so first of all, everybody knows right now the permanent magnet motor is very common in industry, and it refers to different type of motors, especially in every motor that has a magnet. It's in its structure, so it can be referred as a permanent magnet motor. Of course, we have BLDC, PMSM, PMVC, and other type of things. And today we are going to discuss mainly on the PMSM, which is the Permanent Magnet Synchronous Motor. So this motor has quite some advantages. First of all, it has the very good efficiency, which is comparable with the other motor, and interestingly, it's higher than the induction motor, which is the big motor in the industry. And then in the same size of the machine, comparing to induction machine, this will provide the higher torque and the higher power. So it means that the torque density and power density is high. And I'm not going to say it comparing to induction. It has this type of motor has a small, very low torque ripple, but again, it's of course it's going to be higher than the one that induction motor has. But again, it's small, and therefore the noise and vibration is small. Another thing which is important in this machine, it has a very fast dynamic response, which is important for the control system. People who's working on the drive and control of this machine, they may notice this one. So I'm not going to talk about the principle because we talked it before in our previous. I'm going to jump into the problem and talk about this operation, the principle of operation. Let's look at what happens mathematically in the PMSM motor and how torque is generated in a PM motor. Assume you have a motor, and due to the rotation, the back EMF is generated. Ideally, we like to have the sinusoidal waveform. The reason for this one we will see later. And then if you apply the current to the machine, which a three-phase sinusoidal waveform, and then you can generate the torque. And the torque equation shown here, it's simply the multiplication of the voltage and the current divided by speed. And if you see, despite that the current and the voltage is a sinusoidal and is changing by time, you are going to reach to the very smooth torque, which is a line and with no distortion or no ripples. So this is the ideal case. We are looking for it, and very interesting. That's to make this machine very interesting for us. But in real life, it's not like that. So in the real machine, the back EMF is not sinusoidal. So this is what happens. So when the back EMF is not sinusoidal, if you use this Fourier transformer, you can show it based on some harmonics, and then by calculating the torque again, you are going to see the torque which is fluctuating, which is distorted and has some ripple. So this is the torque ripple that you are going to see in the real machines. And so designer all the time try to reduce this torque. So how we are going to do this one? One of the ways that we can reduce this torque is to make sure that our back EMF is the has the sinusoidal waveform. Okay, so how we can do it? How we can generate sinusoidal back EMF? It's a very tricky thing. Okay, there are normally the important thing is for us is to generate the air gap flux density which has the sinusoidal waveform. If we are able to do this one, then simply we can generate a back EMF which has the sinusoidal waveform. So, and this one can be done with sizing the magnet. So, in previous webinar, we saw that the magnet dimension is very important for permanent magnet motors performance. So one of its importance here is affecting the waveform of the air gap flux density and consequently the back EMF waveform. Another way that we can a little kind of help to have the sinusoidal back EMF is to make sure that the windings see the in the way that it has the sinusoidal waveform. So in this one, it can be done simply by using some certain type of winding configuration. Okay, so in this presentation, so we are gonna discuss these. We are gonna discuss these two problems. Okay, and for this purpose, I'm gonna use a 2 horsepower machine, which is surface mounted magnet motor, and the specification of these motor shown here. You can see the rated power is 1500, which is a 2 horsepower. The rated speed is 2000 RPM, and the geometrical dimension you can see like the outer diameter of stator is 132, the air gap is 0.7 millimeter, and kind of thing. And to reach the purpose of this presentation, we made we decided to study the two main things. In the first one, we are going to see the magnet span. We are going to change the magnet span from the 50, 60, 70, 80, 90 degrees and see how the back EMF is going to change. Another one, we are going to use the two different type of the winding, which one of them is the full pitch single layer winding, and another one is the short pitch double layer winding. So these two type of winding, we are going to study these two things in our presentation. Before going to this one and simulate the motor, we are going to simulate this motor. After this one, I'm going to show you how to first model the machine in the software, and then we get the results. And we are going to discuss more about it. Okay, but before going to that, we have some parameters here. We have the slot pitch, which is the distance between the middle of one slot to the another slot. You can see over there in the right corner bottom, it's a slot pitch. We have a pole pitch, which is the middle of the one magnet, the distance between the middle of one magnet and to another magnet. In this case, the surface mounted magnet normally says it's 360 divided by the number of the poles, and it's represented based on the degrees, electrical or mechanical. And important parameters for us here, the magnet span, which is you can see in this figure, is the length of the magnet that covers in the rotor side. And so we are going to discuss about more about this stuff in the simulation part. And back to let me switch to the simulation. I'm going to show you first how we are going to simulate and what type of result we are looking for. This is EMWorks 2D. It's software, 2D software. You know, everybody which is working with the motor, they know that we can easily use the 2D simulations much more effective for us in terms of the time, and it gives enough accurate result for us. So we have the model. This is the SolidWorks environment, and this EMWorks 2D can be installed inside the SolidWorks. We can use it as an add-in, and you can work on it. Once you install it, you will, and you created your model in the SolidWorks, you can run a study on it. It's very simple. Somebody may ask how we are going to create model. We showed it in the previous one. You can do it by yourself, or we had the previous software that we had in template base. You can do it, but this one is not limited to a template. You can create any model here. Then you came here, you click here, and you choose the study. Then you have here the two options, electrostatic and magnetostatic. Of course, we are looking for magnetostatic study because we are going to see some of the torque and back EMF and this kind of thing, which easily can be achieved by magnetostatic. You can have parameterization to seeing the couple of position or one position. You can check the computation of the circuit. Then here the level of accuracy that you are looking for. Normally we put it in 2, it's enough for us, but if you are looking for a higher accuracy, you can put it in 3. Then here you have to select the coordination system you are using for it. Here easily, if you are the SolidWorks user, you can simply select this coordinate system you already defined. And here, since the length of the machine is very important, the length in the Z direction, you put it there, and you can, for example, any number. I don't know, for this machine, I know it's 74, but up to your machine design. So you put it there. Once you did this, you can simply click here, and it's gonna create you a new start. Okay, it may take a little time, just a couple of seconds. Oh, sorry, my computer getting slow. Okay. Yeah. Sorry guys for this one. It seems that my laptop is freezing. Okay. Once you define the study, it's gonna create a tree for you. In this tree, defining a study, it's very simple. You have your surfaces here, for example, the rotor components, the magnets, all is defined here. I defined it in the SolidWorks model. Then you just need to apply. Even let me show you. You have to define also the outer area, just in case if you want to apply some boundary condition on it. Okay. First, you apply the materials. It's very simple. You just select the whole component or one of them. You can just say apply material. And for example, it's magnet. Opens here the material library. It's already classified based on the type of the material. For example, you can apply this one. And you see it's going to come here. You can define the coercivity direction for this one. It's very easy because it's magnet. You can choose for cylindrical or whatever it is for magnet. You can apply A for this part. I have some interested material here. I used it. And even if you, for example, you choose for the rotor core, you can apply material, for example, such as M27. which is the, sorry, not here, here. And then you can easily edit material. You can come here if you want to apply lamination. You can easily apply the lamination in Z direction or whatever it is. You put the stacking factor. So everything is simply there. You can do whatever you want to do. And once you apply the material, another section is to apply the load constraint. Normally we apply this to the edge of here, the zero vector potential, which is the common thing for the motor analysis, and that's it. You just need to select this edge. After that, you need to, let me just hidden this part of the outer air to see the properly. Okay, and then you define the coils. It's very simple. You can define the solid or wound coil. You define it like by selecting the surfaces like this, and then putting the number of the turns, number of the current if you want, and the diameter can be AWG, or you can directly change this one. And if you want to include inductances, you can check this one. Let me show you. I already defined one here in this one, and I defined 3 phases. Okay, simply I defined at the beginning it was like this. Okay, you can define this one, 6 coils, which is, if I want to show it, see, this is the A plus, A minus, which refers to a go and return of phase A. Then I can simply add it to the phases and define the phases simply. And I defined this one. And this is for defining the coils. You can do it whatever it is. Next step is to define the visual work, or if you want to calculate the torques or calculate the force, it's up to you. You can easily just click and define visual work or Lorentz force, depends on what you're looking for. And then you have to just select the parts that moving, then you can select them, or the parts are not the moving parts that you want to calculate the force or torque. You can switch between force and torque, and even you can have both of them. It's up to you. Then you can define at which coordination you want to do. It's based on the coordinate system of the general coordinate system of the model, or whatever it is. So once you did this one, then after that you have the mesh. If you want to apply mesh control like this one, we applied the mesh control. You just need to apply mesh control. Then it gives you, you can select the surfaces. For example, I can select here, or you can select the edges. For example, if you, for example, I'm just giving example, you this edge, you can do it. Of course, it's not common to do that, but normally we prefer to have like in this edge. It's more common thing. It's up to you. Simply, you can select edges or surfaces that you want to have the finer mesh to get a better result. And once you finish, another part is to do the parameterization, because it's a magnetostatic analysis. You can do the parameterization easily here. Let me show you, for example, in this one, what I did, I defined, we have the parameters, like here, we defined it before. It's the rotor angle parameter. You can change the rotor angle and calculate the field. Simply, you can get some result. I defined, for example, here from 0 to 60 degrees, I rotated the machine and calculate inductance or other results. Another study from here, I wanted to calculate the torque, so therefore I added the, sorry, not this one, the torque. I just, yeah, I added the coils. Then at different rotor position, I applied the different currents. It's very simple. If you want to apply the current, you can enter the currents by hand, or if you want to create something, you can load the scenarios. Here I load the scenarios. from the file. It simply comes here. You just need to click here and open whatever it is. For example, I already defined something here, excitation, and then I just load it and it opens. It brings your scenarios here. You can run the simulation. Okay, let's look at some of the results that I got from here. You can see any type of the result. You can see in the result table, or you can create it simply here. For example, in this one, I saw the carrying torque. It's carrying torque. You can see it's just I do it for the 15 degrees. It's very symmetrical thing. And if you want to see the field analysis, you just need to click here. You see the field analysis. If you want to do some options, you edit them or whatever it is, show some chart options or settings that if you want to look for it, you can remove the lines if you want and make it simple. It's up to you, and that's it. That's very simple. So I'm going to hide it again. Another thing that another type of result I saw, it's here, it's the torque. Here I created some of these results. Yeah, you can see the result here. There's a result table, all the results here. You can simply, for example, if you're looking for the torque. See, we apply the sine wave current, but you see the torque is fluctuating. Okay, these are the kind of things that you are looking for. Maybe you are interested, like this one, you have here flux linkage. You can see that it helps you to simply create, and since it's a 2D simulation, it will be much more faster and stronger. Okay, I'm going back to the simulation and continue with the result I got. So I told you that we do two studies. First one, we change the magnet's dimension, and another one is the change of the winding. Okay, so in the first one, we change the magnet dimension from 50 to 90 by the 10 degree. And see what will happen. Okay, see, this is the back EMF of the different cases. We generate the 5 model, each one with a different magnet span. At the first one, 50, second 60, and go on to 90. You can clearly see here that by increasing the magnet span, you simply can, your back EMF waveform is changing from the sine wave toward this square wave shape. You can see, for example, for 90 degrees, almost a square wave shape, or for the 80 is a trapezoidal. It's very clear from here that the magnet span has a very great, significant effect in the shape of the wave. So, but it's not completely sinusoidal. Let's see, to see how much a waveform is close to the sinusoidal, we normally use something called the Fourier transform. And you can see here in the first picture at the left top, which shows the fundamental harmonics, which is the main harmonic contributing to the torque of the machine. You see, we generate by increasing the magnet arc, we are increasing the fundamental harmonic value, which is very useful to generate the torque. We will see in the next slide how it will affect the torque. And the second picture is the value of the different type of the harmonics, different harmonics number for different arcs. You see, for example, for harmonic number the third harmonic, the fifth, seventh, ninth, and 11, and they had based on the arc, the magnet size, their value is changing. For example, you can see that the fifth harmonic for the arc, the 50-degree arc, is like more than 5 volts here, but for the arc of the 70, it's almost 1, which is a small one. So it's very important. And one criterion to see this one, it's the PhD, which is the ratio of the harmonics to the fundamental harmonics. And this one, by showing this one, you can say that it's the criterion to say that how much a waveform is distorted or is deviated from the sinusoidal. And you can see clearly here the 60-degree arc, the machine which has the 60-degree magnet span, has the minimum THD. That means that this machine has the most similar waveform to the sinusoidal comparing to the others. And by increasing the magnet size, this THD increases, which means that creating the higher harmonics. So what is going to happen? What does it mean? Let's see it. This shows the torque and the torque ripple of the machine. What you can see here, by increasing the magnet size, magnet dimension, which is here the arc of the magnet or magnet span, you're clearly increasing the average torque generated by machine, which we expected, because by increasing the magnet span, you're increasing flux density. But there is a but here, and it's by increasing it. If you see in the figure, the right figure, you can see the torque ripple is also increasing. So it is true, by increasing the magnet arc, we are increasing the generated torque, but at the same time, we are increasing the torque ripple. And if you see here, the machine with the magnet arc of the 60-degree has the minimum torque ripple, which had before the minimum THD. So as you can see, the importance of this reducing the harmonics is very clear to reduce the torque ripple. And what we can conclude from this one is that we need to make a trade-off between the average torque and the torque ripple. So another way that to control or to make the sinusoidal waveform is to use the short pitch winding. Actually, how it can help to us is that this winding structure can help us to remove certain harmonic. It's not to generate a sinusoidal waveform, it's to remove certain harmonics. And how we do it, we have something called the pitch factor. So what is short pitch, first of all? Normally, in the winding the system of the motors, we have the 180 electrical degree distance between the two sides of the coil. If you see that the full pitch coil, it means that the one side of the coil is under the N, but another side is under the S, which is the 180 electrical degree. So the N, we make sure that one side of the coil is under the N pole and another one is. But sometimes we intentionally reduce this one, and you can see the short pitch coil in the second picture. So how this going to help us? Okay, we have something called the pitch factor, which is calculated by cosine multiplied by N is the harmonic number and theta is the short pitch angle. And short pitch angle is this distance here that we just reduced we just displaced the coil side. Okay, for example, if you want to eliminate the fifth harmonic, okay, means that you want to see the Kp5 equal to 0, you just need to make sure that this here 5 theta divided by 2 is equal to 90, and it means you need to make a 36 electrical degree reduction. But in reality, it's not possible because this angle is not completely in our hand. It just changed based on the number of slots, and it doesn't have that much flexibility. But let's see how it will be. So what we did, we had a single layer full pitch, which is the theta 0, and this can be interpreted to double layer full pitch, both of them almost the same, against the double layer one slot short pitch. You can see what's the difference. The difference is here. The coil used to go 1 to 7, 2 to 8, but now it goes 1 to 6, 2 to 7. It's a simple difference, okay? We make one slot shorter, and which is this one slot shorter is 30 electrical degree for our cases, which is the 24 slot 4 pole. You can see the differences that come clearly here, okay? So by doing this, you can see the waveform is getting more smoother. You can clearly see from here for the R16, and if you compare it with this one, which is here for the 60, then you will see here it's a little smoother. The same goes for the 70 and 80. Let's compare it carefully, okay? What happens? When you use the short pitch factor, your pitch factor is changing. You will have the different pitch factors for the different harmonics, and it is 0.96 for the fundamental harmonic. And as you can see here, the machine with the short pitched winding has the small lower value of the fundamental harmonic, which consequently is going to reduce the torque generation. And you can see this short pitch is going to help us in terms of reducing some certain harmonics. If you see these three pictures for the different machines, you can clearly see that from harmonic number 7 and the 5, the 5th harmonic and 7th harmonics, in all the time, all cases, the value of the machine with the short pitch, the value of the harmonic is less than the full pitch. So it certainly reduces this harmonic. It kind of eliminates this harmonic. So what happens in terms of the torques? As I mentioned, it's going to reduce the torque. Average torque will be reduced because we reduce the back EMF fundamental harmonic by using the short pitch. But at the same time, it's going to reduce the torque ripple. You can see in these two pictures clearly for the different magnet R, using the short pitch winding is reducing the harmonics. So it's very clear. So you can see clearly what is going on here. So let's make a conclusion, okay? As a conclusion, the sinusoidal back EMF is essential for smooth operation of the machine. You saw that if we have harmonic and if the waveform, it's not sinusoidal, we are going to create the ripple, which is the noise and the losses. Then we saw that here that the magnet span has very significant effect on back EMF waveform, and is the most determinant parameters to generate sinusoidal back EMF. So if you design the PMSM, Permanent Magnet Synchronous Motor, make sure that you do something, you generate you choose the magnet span properly to get what you want. And another thing is that short pitch winding can help in this way to you to eliminate certain harmonics. We saw that one slot of reducing the pitch, the pole pitch, can simply help you to remove in this case, I'm emphasizing, in this case, the 5th and 7th harmonic pitch kind of consequently reduce the torque ripple. So, and as a suggestion, I have to tell you, uh, all the time for us as an engineer to design a machine, we need to do trade-off between what we are looking for. So if you are looking for to get the high torque and the minimum torque ripple, you have to make sure that you do trade-off and you play with magnet span and the type of the winding to get your best. Okay, thank you very much. I'm gonna return the screen to my colleague. He's gonna continue with you, and after that we will answer the questions. Cal?
Thank you, Mahmood. Thank you very much. So now we're going to discuss some of the learning resources which EMWorks offer. So EMWorks offers various types of learning resources. In the zone of free learning resources, with the software purchase or trial, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition to that, we also post many application notes, blogs, and application videos on our webpage and social media channels regularly. I would encourage everyone to subscribe to our social media channels to check out the latest videos, events, or any information updated by EMWorks. We also offer paid customized training sessions to all the users of EMWorks software. Anyone who is interested to get more information on our products, including trial, quotation, can go to our Contact Us page on EMWorks website. Select your appropriate category and submit your request. One of our representatives will reach out to you soon. Before we answer your questions, I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you again, and we look forward to see you in our upcoming webinars.